Okay, now that the midterm is all done and set to be graded over the weekend, we can move on to another way to minimize the number of gates being used in a logic circuit. How is that spelled? Carnot. Another method to do gate minimization is with Carnot maps, otherwise known as K-maps. This is a gate minimization technique that does not involve Boolean algebra, and Boolean algebra has its challenges because you have to get sometimes creative in how you manipulate a Boolean expression. A Carnot map, let's say here is a, we'll do a simple 2 by 2. No, that's usually done. X and Y. And you have 0, 1, 0, 1. Basically, what you do is you take a state table that you want to minimize. Let's say here X, Y, out, and you got 0, 0. And say you want to do 0, 0, 1, 0. You would have the put the combination, each combination in the state table in the Carnot map. So 0, 0 is 0. 0, 1 is 0. 1, 0. And 1, 1. Y is, the values of Y are here. Values of X are here. And then you simply match up. This is X, the X term, and the Y, the X literal and the Y literal. This is Y, Y prime, X prime, X. So you just go match up where the ones are. It's X and not Y, because it's in the not Y column and the X row. You can make it a little bit more complex with more 0, 1 is a 1, 1, 0 is a 1, 1, 1 is a 1. Now you don't do, this is where the minimization comes in. You don't do, you could do individual ones and do for x, y, or not x, y. Okay. But obviously that's not minimized. You could then use Boolean algebra to minimize this, but what the easier way to do it, where Karnaugh maps make life easier, is you can group ones together. There's two groups. This one is x, and it doesn't matter the y. So x and y, or y. It doesn't matter the x for this group because it's both x. X could be either 1 or 0, and it just is the y. So that's the expression minimized. And this bears out that this is the state table for a OR gate. So you can use it to minimize that. More frequently, Karnaugh maps are used with 3 and 4 variables. Theoretically, you could do more than 3 variables, but you get into 3-dimensional Karnaugh maps, which are difficult to manage with 5 variables or more. But let's do a 3-variable let's see here. And let's see here. 1, 0, 1, 0, 0, 0, 1, 1. Okay. Now let's laying out a 3 or 4 variable Karnaugh map is a little bit more complex. You have 2 variables on each side. You can have up to 2 variables on each side. X, Y, and Z over here. And it has 8 combinations. So you have 8 cells in the Karnaugh map. Okay. Here, you're not counting in binary. You're changing 1 bit at a time as you go across. So the first one here is 0, 0. Change 1 bit to 0, 1. Change 1 bit again to 1, 1. And then change the last bit to 1, 0. Okay. And of course, over here on the X side, that's 0, 1. Now, this is the X prime. This is the Z here, because the Z is both 1s. and z prime, and y and y prime. Okay. Now to translate this into this state table into the Carnot map, you look at the same way as we did for the 2x2. It's just with 3 variables. So 0, 0, 0 is going to be 0, 0, 0, 0, 0, 1, 0, 1, 0 is going to be over here. Let's just do the ones and fill in the rest with zeros afterwards. And 1, 1, 1 is going to be, oops. Here. And 1, 1, 0 will be here. And then the rest are zeros. All right. Now the same approach from the 2x2 K-map is used here. You group groups of 2 together. And then you have the group of 1 in this particular instance. So you look at the groups of 2. X. This one has the X and Y, but it doesn't matter on the Z. So it's XY. Here it has Y and not Z. I'm sorry, not Z. Yeah, not Z and Y. And the X doesn't matter. And then you have the 1 that has the X prime, Y prime, Z. Yeah. With K-maps, you can group ones together in groups of powers of 2. So 1, 2, larger maps you can use 4 or 8. And they have to be next to each other. Diagonal doesn't work, so you can't do these 2 together. That makes it so that, like in this case, the X, these 2 ones here, the X is 1 and the Y is 1. Z doesn't matter because it's in both the Z and Z prime space. So it's just XY. Here you have in this one you have in the Z prime space and the y prime and the y space, and the x and x prime don't matter. So the x is not in that term. This one is alone, and so you can't. You're stuck using all three literals. Basically, if on a three variable K-map, a group of one has all three terms. A group of two has only two terms. A group of four has one term. And I'll do that in just do that one in just a minute. And then a group of eight just has a one. If it's all ones, then it's just the output is going to be a one regardless of what the variables are. Yes. For a three variable K-map, yes. A group of four would be one term, yes. I'm sorry? Oh, X is all of these. Yes. X and X prime, or X and Y prime are not. The Y prime is not included in this in this group. Yeah, the second group is in the Y section and the Z prime section, and the Y X and X prime don't matter. Okay. This is getting a little bit cluttered, so I'm going to erase it. But we'll do a yeah, just all right, let's see here. Now let's do yeah. No, no. One, yeah, one, yeah. Okay, let's do this one. This one's kind of a weird case. Yeah, 0, 0, 0 is 1. 0, 1, 0 is 1. 1, 0, 0 is 1. And 1, 1, 0 is 1. Now, keep in mind that this is Z, Z prime, Z prime. Notice how Z prime is broken up into two sections. You can think of that as being wrapped around, putting this on a cylindrical shape instead of flat on the whiteboard. So you could do this, where these come around to this other side over here. So you have a group of four. And that would be a group of 4 is only one term in a 2 by 4 K map. So it would be just Z prime. Because of the wraparound. It wraps around from going this way, comes into over here. Okay? It also wraps around going upwards and downwards. But you don't really get into that until unless you have a 4 by 4 K map. As you can see, this group, it's all in the Z prime. It doesn't matter what Y is, and it doesn't matter what Y prime is. It doesn't matter what X or X prime are. So it's just Z prime. Now let's go ahead and add a term here, 1 here. You can add that, and then you have where it's X prime, Y prime, and Z doesn't matter. So X prime, Y prime. I see some looks of not sure if they understand. You OR the groups together to make the final expression. You have the one group that's the Z prime, and this group is just in the Y prime and just in the X prime. It's not in the Z prime or Z exclusively. Okay? Now we'll go on to a 4 variable K map, which has its own little quirks to it. Let's do W. And then let's see here. Now, let's just do X, Y, oh no. W, X, Y, Z. All right, and again, start with 0, 0, and then change 1 bit at a time. Likewise on the side. 0, 0, 0, 1, 1, 1, 1, 0. So you have all combinations. All right. And this is W, W prime, because the 1's for the W, 0 for the W primes. You have X, because the 1's here, and then the 0's for the x prime. You have y prime, z, and z prime. All right. So let's just put some ones in here. Now fill in the rest with zeros. Now here we have that situation where you wrap around from the top to the bottom and from side to side. So you have this group of 4 here that is the 4 corners. Yeah. I'm sorry? Oh, I'm sorry. Missed a spot there. And another something that bears saying. Me included. But I digress. Anyway, so you have this large group that has 4 1's in it. It's the 4 corners can be grouped together into one group. Yeah. Oh, where these go? 1's are x, and the rows with 0's are x prime. Likewise, 0's for w prime, 1's for w. Make sense? Kinda? Same situation. Y has 1's, y prime has 0's. Z has 1's, z prime has 0's. Okay? What other groups could we do? X and W, these two? Okay. Which leaves us with 2 adjoining ones. You want the minimum number of groups possible. You could make this group here, but it would be redundant. It wouldn't be a minimized grouping. But same with this group here. So so we'll just do the large group of 4, which is z prime and x prime. It doesn't matter the w or the y. So x prime, z prime, right? See how I got that? It's for the four corners, for all four. Yeah, x prime is up here and down here. Z is down here and down here. So it matches up the four corners. Then you have x x and y and w prime, because they're all in the w prime, they're all in the x, and they're all in the y. Z and z prime don't matter. So plus w prime x y. Anyone want to hazard a guess what the grouping, what the term for this one is? Wx, this group right here. I think I heard it. W X Z. Yeah. Typically go in alphabetical order. And that expresses that Carnot map. Let's see here. Where things might get a little bit weird is when you have a situation where you don't care what the output is. Now, the difference between a truth table and a state table is truth tables only have two values, true or false. A state table can have multiple states. For example, if you don't care what that is, that's a 1, that's a 1, that's a 1, that's a 1, 0, 1, 1, 1, and 0, 0, 0, 0, 0, 0, 0. You don't care what it is. It doesn't matter. It doesn't matter to the circuit. So you can count that X in there, or should I say DC, don't care. Yes, let's not confuse that with the X literal. Don't care. Because you don't care what it is, you can count it as a 1 or a 0, depending on what is more convenient as far as grouping ones together. So you can make this a group, this a group, this a group, and this a group. Again with the wrapping. So you have 4 terms here. Yeah, 4 terms. So here you have x, y, or w prime x, and what's this term here? This one here. No, x doesn't matter. It's x and x prime. So w prime y z, yeah. And this one? X, y prime, z. And finally, this one here. The two bottom corners. W, x prime, z prime, yep. That, you know, say, and this wouldn't change anything, but say this was a don't care as well. Yeah, you can leave that. You can consider that a 0 and that a 1. It doesn't matter. Yeah, it could. You choose the value for the don't cares that's most convenient for you. And in this case, just choosing this as a don't care, this don't care as a 1, works just fine. Any questions? We got about 5 more minutes. That's the basics of Karnaugh maps. Let's see here. Oh, when you look at one way of, I forgot about this. One way of expressing what you want to find in a K-map is using the sigma notation. Am I backwards? No, that's right. All right, so this would be 0, 0, 1, 1, which is 3. Yeah, I did that. 0, 0, 1, 1 in binary is 3. Okay? 0, 1, 1, 0, 1, 0, 0 is 4. 0, 1, 0, 1 is 5. 0, 1, 1, 0 is 6. 0, 1, 1, 1 is 7. Oops. 1, 1. Actually, let's do this one next. 1, 0, 0, 0 is 8. 1, 0, 1, 0 is 10. And 1, 1, 0, 1 is, what is that, 13? 13? So when you are given an expression as a product of min terms, a sum of minterms, you take those numbers, convert them to binary, and then place ones where the binary numbers work. So let's look at a more simple example here. Say you have with 1, 3, 4, 6. And this is a 3 variable expression. So you have x, y, z. Zero, 1, 0, 0, 0, 1, 1, 1, 1, 0. So 1 would be 0, 0, 1. 3 would be 0, 1, 1. 4 would be 1, 0, 0. And 6 would be 1, 1, 0. And then see how I did that with converting it to binary? This is why number systems are important. 0, 0, 1 is 1, so a 1 goes there. 0, 1, 1 is 3, a 1 goes there. 4 is 1, 0, 0, 1, 0, 0. And then 6 is 1, 1, 0, 1, 1, 0. And then you would group them like so. And then you would have, let's see, what is that? Z, x prime z plus x z prime. I'm trying to go quick because we're running out of time. But you see an expression such as this, and then it turns out that that's the equivalent to x exclusive or z. But yeah, you can convert the numbers of the minterms into binary and easily find where the ones go, and then group, and then write the expression out. Okay? I think that's about it for time for today. But I guess have a good day.